So hello everyone and welcome to this next lecture. So this is the continuing lecture in the DC to DC lecture series, and in the last lecture I had edited the parameters of the Chook converter. So in this lecture I'm going to continue and I'm going to add more features, such as I'm going to add a control file to it. So before I start this lecture, as before, a little bit of background. If you are interested in these kind of video lecture series, however you find these lectures a little too light, I do have a comprehensive course on how to simulate power electronic circuits using Python, and in this course you learn just about everything there is needed in order to simulate. That is, how to install software, a little bit of basic theory, and finally a tutorial on simulating a buck converter. So if you are interested in something more comprehensive, this is an option. If however you do not have the time also to follow most of the lectures, but you want the simulation files and you could use it for your own applications, you can download some of the files from my site, which is Gumroad. The links for both of these are provided in the description of this video, so do check it out if you're interested. So let me get back to the lecture. So as I said before, we had edited the parameters of the Chook converter, and this is a Chook converter that we drew in the very first lecture. Now let's continue further and add a control to it. So as I said before, in any converter you must have some kind of control, at least for achieving switching. So let's go back to the main page and go to the control file. So first we need a control file. So as of now, the only thing we have is the circuit file, that is a circuit schematic. So let's add a control file. For that, let's go over to my editor and let's pick out. You can pick out from anywhere, just pick out from the buck converter. All we have to do is pick out the gate signal.py file. So let me go to my file browser. Let me go to buck converter and let me choose gate signal and gate signal underscore desk, which is a descriptor file. Let me paste it in Chook converter. So if I go back to my editor, now these two files should appear, and they do. So to begin with, I just have to take the gate control and we just go through it. So we have a switching frequency of 10,000 Hertz or 10 kilohertz. And as we know, we've already covered all of this. We are setting the modulation signal to an open control mod signal from the previous lecture, where this open control mod signal was where we were varying the modulation index using another control file. So we still don't have that. So let's comment this out. And let's bring in this code which just sets the modulation signal or the duty ratio to a fixed amount of 0.3. Then after that we are performing pulse width modulation. So this can stay as it is. So let's add this file. So we are in Chook converter and we add the gate signal.py. So all I have to say is pwm and we need to configure it. So for that, all we have to do is just upload the gate signal.underscore desk.csv file. So these are all the variables, nothing new. We can just go ahead and start running the simulation. So with this, let's go back to the main page and let's go back to view output. So in the view output, we are now ready to run the simulation. So this is a simulation where I'm running it at a constant modulation index. So you can say almost open loop, except there's not even a change. There's not even an open loop control. So there's not even a change in the modulation signal. The modulation signal is constant. So let me click on the run button. So apparently there is an error. So let's go find out. The branch with ammeter L2, inductor L2 does not have a resistor. So let's go find out. Where is L2? And yes, indeed, the error is right. This branch is a pure zero resistance branch. The inductor has no resistance. The ammeter has no resistance. So this is an error. So the simulator picked it out. So let me go and add a resistance. Let's call this L2. Right? So let me process it, or let me save it. Now that I have made a change, you must go back to the circuit file and process the circuit schematic. Remember, any change in the topology of the circuit needs to be processed. This is to ensure that all the objects are updated and the database is updated. So now we have to edit the circuit parameter, because remember, a resistance has a default value of 100 ohms. That's way too large. This is a parasitic resistance. So let's come down to resistor, and here's the resistor. So we have resistor L2, which is 100 ohms. So we have to change this. We can make this 0.05. can change it to any value you want, no real problem. So with this, we are ready to run the simulation again. So let's go back to the main page, to view output, and let's click on run again. This time apparently it's working, but do not take that for granted. Go over to the command line and make sure that there is no error, and there is no error. So we are good to go. So let's start by plotting some values. So most important, always the best thing to plot is the output voltage. So let's do that. Let's add the output voltage. Output voltage plot, very nice, we've done it before, so it is already available. And here all I have to say is voltmeter VO, and let me call this VO, and let me save the waveform and click on done. So with this done, we can just go plot it. So let me go to the command line, make sure nothing is wrong. Actually, you don't have to do that. The main thing is when you actually start running the program. So let's check out the output voltage.png file. So first things first, you see a negative voltage, and as I said, this is expected. The reason, because that's how the Chook converter is. Okay, remember, how does it work? Switch is turned on, current flows in the clockwise direction. The capacitor will also discharge in the anti-clockwise direction. Both of them are feeding current into the switch. When the switch is off, the capacitor charges, right? But the inductor will now, the capacitor will, or rather the inductor charges, or rather the input charges the capacitor through the diode. Now the diode conducts. So therefore the current flows in the clockwise direction again, but through the diode. The inductor, which was first initially being charged by the capacitor, because the capacitor was charging current through the inductor in the anti-clockwise direction, will continue to flow, because remember, the current through the inductor cannot change instantly, and it cannot reverse direction instantly, which means this will continue to freewheel. So the current in this path, that is through this path, which is also includes the output capacitor, is anti-clockwise, which means the current in this capacitor is flowing from down to up, and that means that the positive polarity of the capacitor is downwards, right? So we are still measuring a voltage, whereas the output voltage we measure is still with respect that the positive polarity is above. This is because it's important to show that the output voltage is negative, right? We cannot hide that fact. If we reverse the polarity of the voltmeter, we'll get a positive voltage, but that's actually misleading. That gives you the idea that the Chook converter doesn't invert the voltage, but it does indeed invert the voltage. So this result is okay. So let me just run it again, because it would have settled further. So let me go back and run it. So yes, it has settled. So let's go and find out what the value is. So it's, you see, it's between -4 and -6, so it's around -5, right? So how do we know? Let's go calculate this. So as before, with the Chook converter, you have 12 into 0.3 divided by 1 minus 0.3, and this is the result we get, right? This is the formula for a Chook converter. I won't go into the actual theory of how this came, but this is pretty much similar to a buck converter also, right? Buck boost converter, sorry. So using this value, we get a voltage of -5, and this is actually the voltage that we are seeing, right? This is around -5. So therefore our converter simulation is working correctly. So let me just switch it off and let me save it. So let's go and plot some more currents. So what are the currents we can plot? We can plot the ammeter L1. These others are the same, so we don't have to plot it. We can plot the ammeter L2, and we can plot also the ammeter C1. So let's do that. Let's plot all the currents together. Currents, and here I will say ammeter L1, IL1, save, and as I said before, let's start giving it a little bit of a scaling factor just so that we can actually start capturing it. So I'll give it like 0.05 or rather 0.02, save the waveform. Ammeter C1, we do need it, so let's plot it, and again 0.5, save the waveform. And what else do we need? Let's go back here and check. Inductor, I actually forgot to measure the current through the switch. Maybe I should do that. next, but I think this is all we need. So let's go back and plot this. You can say done and plot. So initially there'll be a very large current because it's pretty much impossible to make out, but still I prefer to do this so that then I can pick out how much I want. So let's choose somewhere from 0.4 to 0.401. Let's zoom in. So 0.4, 0.401, and let's plot it. So let me go to the file browser and let me choose this current. So this is the voltage, rather this is the current waveform. So I am surprised that we still see an overlap. Let me just go back and check, but you can't see. So you see what has happened. The inductor current, that is the blue line, this is the inductor current actually the blue line is superimposed, but you see that their inductor current IL1 is the blue line here and it continues. The orange line is the inductor L2, which is scaled. Remember, the only reason why these are different is because they are actually scaled, but these two will be the same. Right? And we can plot it again to confirm. And the third one is the capacitor current. So the capacitor current, if you look, when the switch is turned off, alright, when the switch is turned on, this is when the switch is turned on and the inductor current, the current through the inductor L1 increases. At this time, the capacitor is discharging through the switch, and that is why the current through the capacitor is negative. If you look, this current is negative, but it is almost symmetrical to what you see here. At the same time, the current through this inductance L2 is increasing. Why? Because the capacitor C1 is charging this inductor. When the switch is turned off, the current through the inductor L1 starts freewheeling through the diode, and instead it starts flowing through the capacitor, and the capacitor also starts discharging. And this is why these two currents are the same, right? Because actually they are the same current flowing through, right? The inductor IL2 also starts falling because the inductor L2 is now freewheeling through the diode and is charging the output and is feeding the output. So this is the working of the Chuk converter. Now, there is a very interesting phenomenon that happens specifically with the Chuk converter, and I will show you what that is when I plot the two inductor currents. Right? Now, I am deliberately going to plot them at the same scale. So I'm going to choose a scale of 1 for the inductor L1 current, and for the L2 I'm going to choose the same scale because I want to show you an interesting result. This is done, and let me plot it. Of course, we know that we can plot it for this zoom, so let me just go and plot it for the same factor or the same time window. So let me go to the file browser and we have inductor currents. So you see, these are the inductor currents. Now the inductor currents, as you can see, they have a very interesting phenomenon, and that phenomenon is that they have the same ripple. If you look, the ripple is the same, and I would encourage you to actually calculate how much would be the ripple. The ripple in it, this is not a coincidence. This is actual theory. In a Chuk converter, the ripple in the current through L1 is always equal to the ripple in the current through L2, and they always match. So you see, they are always increasing together, they are always decreasing together, and the ripple is the same. And for this reason, these two current inductors can actually be wound on the same core. Right? But that's an advanced concept, we don't have to go into that, but just to let you know that this is how it is. Now with this, I'm going to end this lecture because it is, I think, fairly obvious how we managed to get these results. In the next lecture, we are going to look at the open loop control of the choke converter, where I will change the modulation index to emulate what might later be a PI controller or any other form of controller, right? So, and of course with that I'll also wind up the lecture. So with this I will stop the lecture. If you have any doubts, please do post in the comments or send me an email or message me on social media, whichever is your preference. So I will see you in the next week, where I will more or less conclude on the choke converter series. I hope you enjoyed this lecture, and otherwise see you soon. Thank you so much. Goodbye for now.